you've talked about whether a function is continuous or not in pre-calc, and I think if I just gave you an image, you would easily be able to tell me yes or no. So if I draw, you don't have to write this anywhere. Draw for you that graph. Is that a continuous graph? Yes. Okay. No. Is that a continuous graph? No. Okay. So just looking at it, you guys understand what continuity is, right?
Yes.
Okay. So we're going to get into the little more formal definition of it today. If I ask you for the formal definition of continuity, it's a three-part test. So first, you have to tell me that the function value is defined or that it exists, that the limit at that specific x value exists, and then that parts 1 and 2 are actually equal to each other. Okay? So we're going to go through some different pieces with that, but these are the 3 steps you would have to prove that a function is continuous. Okay? And then there's different types of discontinuity. Do you guys remember from last year the types?
Poles, asymptotes,
and jumps. Good. Good things like this. All right. So let's look. We're jumping down to the graph here. So first example, we've got f of x equals 8 over x minus 5 quantity squared. Right away, do you guys recognize that there's an asymptote if we were to graph that? Okay, so let's sketch the asymptote in here. This is like a really tiny graph. Where would the horizontal asymptote be? 0, yeah, it's 0. Bottom heavy, so we know it's at 0. Okay, now a sketch of this graph. I'm not looking for you to plot the exact points, nothing perfect about it, just the general area of the graph. Since my asymptote is at 5, I need to pick a number on each side of that asymptote. So if I plugged in a 6, what would I get? 6, 8, right? Okay. That's way up here somewhere if I can. Like here. Well, if you're following your asymptotes, you know the shape of your graph has to, hopefully you draw better than me today. Has to be somewhere in there, right? Okay. So I plugged in a 6, I got an 8. I need to plug in something on the other side of my asymptote, so what should I plug in? Yes. And what do I get when I plug a 4 in? Also 8. Okay. So something like that. Is that a continuous function? It's got an asymptote right in the middle of it, so that is not a continuous function. If we were talking about these 3 steps, the first one would not be met. Like f of that specific value is not defined. If I write it down here, you would say f of 5, and you could even just say does not exist. Okay, so you know it's discontinuous. Last year, all you had to do was look at it and tell me, oh, that's not continuous. Now you're going to have to be much more specific with that. Okay, for the second example here, we need to figure out if this has an asymptote or if it has a hole. So what do I need to do first? Factor. What does that numerator factor into? Okay. So I can cancel out my x minus 5s, right? So I'm going to have a hold with this one. So you are now left with y equals x minus 2, right? Or f of x equals x minus 2. What is that the graph of?
Straight line.
Yeah, just a line, right? You guys remember how to graph a line? Y-intercept of -2, slope of 1. But where am I going to run into an issue?
At x equals 5.
Yeah, what do I get when x equals 5? Like if I was to try to find the coordinates for this point, plug in a 5 and what do you get? What? Okay, plug it into what's left to get the actual coordinate.
7. Or 3.
Okay.
3.
Yes. So 5, 3. On your graph, you just need to go over to 5, up to 3, draw a hole, draw your line on either side of it, and you're good. So for the first one, we had an asymptote. Second one, we have a hole. F of 5, again, does not exist. What do you think we're going to have on the last one? Oh, yeah. Okay, so we need to sketch our piecewise graph here. To start with, this says x is less than 5. So I'm going to plug a 5 into that first equation. What do I get? 3. So you said, yeah, good. 5, 3. And is that going to be an open dot or a closed dot? Open. Okay, and it says x is less than 5. So pick another number less than 5. 4, sure. What do I get when I plug in a 4? 2, right? Yeah, okay. All right, is this the graph of a straight line? No, what is it? Absolute value. So where's the vertex of this absolute value going to be?
-2. 0 and -2.
No. Good guesses. Absolute value normally starts at 0, 0, right? And this. That's a shift to the right 2. Okay, so it's going to be over here. So when you sketch your graph, that's like the right side of the absolute value graph, and that's all you get from it. And then you have to know that the left side will be doing that. So it's a little trickier for a piecewise graph. Wait there for a minute, I see processing. Why does it come back up? Okay, so absolute value, remember, is the graph.
Oh, I understand that. Yeah.
Okay.
Wait, how do you deal with x-axis?
Like, how did I know that's where the vertex was? So you remember the vertex is normally at 0, 0. And then graphing, like the transformations,
Yeah.
this just means right 2. So I know that the vertex is now. All right, you still have to graph the second piece. So x is greater than 5. Again, I start by plugging in a 5. What do I get? 1. Open or closed off?
Open.
Open, okay.
It's just 2 left.
Yeah, that's just you do slope from there, or plug in a number bigger than 5. What would you like to plug in bigger than 5? Yeah, sure. What do I get when I plug a 6 in?
3.
We sound so tired. And this is just a line, so connect them. It's going to keep going that way forever. Like the day of yawning.
They should be driving.
Has this not been the longest week ever?
So
Oh,
long.
it's been brutal. Longest day, oh no.
Today has been the longest day of the week.
Yeah?
In the weekend.
It was like a smooth day, but no.
Oh, okay.
I'm looking forward to the weekend.
Okay, that's good. You look like you need a nap. Are you gonna nap this weekend?
Yeah.
Okay.
I'll probably nap
Who
tomorrow.
said senior year was easy?
It's not.
Hard as you.
Like, it was
I was
so
like, junior
hard.
year's the hardest one that you'll have. No, it's the first semester of junior year. It's not hard.
Junior year's
to make your
really
senior
hard.
year. You gotta know it's your senior year and not take all these art classes.
Nah,
Unless you're trying to get into, you're still trying to get to college now. Yeah, my class.
Yeah, that's true.
Yeah, Alex. She's like half to fly.
Say like, I was like, oh, after like, it's supposed to not fun. It's not just
Oh, where are you going?
grades.
Huh?
Where are you going?
Well, then there's
That's nice.
Yeah, big time, man.
Full rides?
Yes.
She got the ring too.
She's got the heart.
She should sit in the throne. She's not worthy to sit in these chairs.
Yeah.
Yeah.
Alright guys, are you ready for more math?
Yeah.
Yeah, we can do this. Okay,
We can-
so each of these graphs, what's the domain of every single one? Remember the whole interval notation thing?
It's infinite, but no 5.
Okay, so negative infinity to 5, parenthesis, union, parenthesis, 5 to infinity. Is that coming back to you?
For the last one, you have to go F5 does not exist.
Yes, I should say that there. F of 5 does not exist. Thanks, Tom.
Maybe Thomas should have.
Okay, so at the bottom, it's just explaining the types of discontinuity that we've already talked about. So we had an asymptote, we had a hole, and then we had a jump. So those are the 3 types. Okay. Do you remember you tell me where it occurs? So it's like an asymptote at x equals 5, a hole at x equals 5, a jump at x equals 5. All right, well, let's turn the page. For me, not for you. Okay. So, 4th one here, let's try to graph this again. This looks a lot like the piecewise graph we just did, doesn't it? What's the only thing that is different?
Greater than.
Yeah, this is or equal to. So I know I'm going to have a filled in dot at 5, 3. 1, 2, 3. But then the rest of it is going to look the same. So I'm going to have my absolute value graph. And then I'll have the other line, which ended up open circle at 1, going that way.
Yeah.
Yes, the only difference is you have a filled in dot.
Oh.
The one we just did, they were both open, right? There's a reason that we did this, I promise. I didn't just run out of ideas for graphs, okay?
Never.
Okay.
Always.
Always plenty of ideas. All right, so on the previous examples, remember f of 5 did not exist.
Also,
Does f of 5 exist now?
yes.
It's 3. So if we're saying the type of discontinuity or why this is discontinuous, it can't be because that value doesn't exist. What do you think is going to be the reason this time? Let's look back.
The limit of 5.
Exactly. So we go back to our 3 choices here. We already did this, that the function value doesn't exist. So now we need to look at this option. Does the limit exist as x approaches 5?
No.
No. The left and the right do not match. So you would say the limit of f of x as x approaches 5 does not exist. So that's a reason for having discontinuity. The type you still know. What kind is this?
Oh, or jump.
It's a jump, yep. You really do need a nap.
Yeah.
Okay, then.
Oh,
That's great.
Yeah.
What if there's two open circles?
Like the
What
last
if there's a
video.
jump?
It is still a jump, yes. What did you
Like,
do?
The last video.
When I'm like, it's my last day with you guys. We're done. Do whatever you want.
after 5, if there's two open fields.
Yes. Good.
so two open, you say F5 does not exist. One open, one closed.
You have to see, does the limit exist or not? Okay. All right, what about domain of this?
All the numbers.
Yes. And remember, notation, you either need to write it negative infinity to infinity, or you can do set notation, which is uglier. It's the squiggly x such that x is an element of the reals. You can just take either of those. Okay? Okay, let's graph again for number 5. Same graph again, pretty much. What's the only thing different? They're not both closed. Which one is closed? The other one, yes. So, yes. So we're back to the absolute value graph, looking like this. But then there, I've got a filled-in dot. Sort of. That's not super. I know, I don't like how small these graphs are. So the only thing that's changed here is what the function value actually is. So what is f of 5? 1 instead of 3. What about the domain?
Negative infinity.
All real numbers. Still a jump, right, for a type of discontinuity. But our reason, if we're going to say this is discontinuous, is because the limit of f of x as x approaches 5 does not exist. Okay? All right. Okay. Let's look at this. So we've got this x squared minus 7x plus 10. That looks a lot like this guy, right? Yeah? Okay, and you guys have both on your page, right? So, when we graphed that, we had a hole at x equals 5, and it was what, 5, 3, right? Okay, so I'm going to draw this, and then 5, 3, I draw my open circle, draw my line, draw my line. So that's the first piece of my piecewise. What do I do with that negative 6 when x equals 5? What does that mean?
Put a hole or a circle, like a dot,
Like a dot? Yep.
at x, at 5, comma, negative 6.
Good, yes. Put a dot down there. Okay, so just looking at it, is it continuous?
No.
No, it is not. It's not one smooth graph. But let's look at all the pieces. What is the domain? Yep, negative infinity to infinity. What is f of 5?
Negative 6.
Negative 6. what about the limit as x approaches 5? 3, yes. So, for our 3 reasons why something could be discontinuous, the first one, f of 5, that exists, so we're good there. The limit exists, but are they the same? No. Okay, so if you were explaining why this is discontinuous, you would say, and I'll write it down below, f of 5 does not equal the limit of f of x as x approaches 5. What do you guys think? Is this a jump or a hole?
It's a whole.
It is a hole, yep. When you just have, it's connected, but you've got the open dot in the middle, that is a hole. Okay. All right, let's try to graph the last one here. So we've got a lot of pieces here. So absolute value of x minus 2 when x is less than 5. We have graphed that before, right? Okay, so let's graph that again. It's an open circle at the 5, 3. And it's going to look just like an absolute value. Okay, so then we've got to graph 2x minus 7, just a line when x is greater than 5. So starting at 5, what's my starting point?
0. Oh, starting at 5.
Mm-hmm. What do I get when I plug a 5 in, basically? 3. So the same thing as I had for my absolute value graph, right? So I've got the open circle in that same spot. And then we want things bigger than 5, so you can either plug in the number or you can just graph with the slope. I don't care. If you plug in a number, you get 6, 5. So it looks like this. Maybe. And then what do I do with the negative 6 when x equals 5? Put a dot, right? Okay. Is it continuous? Still not. Okay. What about domain? What's the domain of this? What is f of 5?
Negative 6.
What's the limit as x approaches 5? 3. So why is it discontinuous? It's a hole, and it's because f of 5 does not equal the limit of f of x as x approaches 5. Okay, we're going to keep working on writing. This is kind of the first steps of understanding the formal reasoning for discontinuity. So we'll keep practicing that, but this gives you at least an idea of where we're going with that. And if you flip the paper over, we are going to start talking about the intermediate value theorem. So I'll give you a second to read what's in the box there. Good, confusing math terminology for you. Okay, what this is saying. So f of x is a continuous function. That's important. We had to understand what continuous meant before we started this. So it's a closed interval. That means we're just looking at a little piece of it. The piece we're looking at is continuous. So for every number n, that's just a y value, okay? Between f of a and f of b. Those are two other, like these are y values also, right? And you can see over on your graph here, there's f of a, there's m, and there's f of b. You guys see how m is in between f of a and f of b? Right? Okay. There exists a number c, and this is an x value. What this little inequality means is that c is in between a and b. So if you look on the x-axis, do you guys see how c is somewhere in between a and b? Okay. What they're saying is that if you did f of c, so if you plugged in that x value, you would get a measure y value. Okay. Easier to see with an example, but I just want to make sure we understand all the pieces that are happening there. Let's look at this graph first, and then I'll give you another one that I think will help a little bit. So if we look at the function here, f of -2 equals -2, right? We have that dot. And f of 2 equals 2. Yet, does the graph ever actually touch the x-axis? No. Okay. Why does this not contradict the intermediate value theorem? Well, what's the very first thing it says in the intermediate value theorem? What type of function do we have to have?
Continuous.
Continuous. Is this guy continuous? No. So, it's not a continuous function. So before we do another, let me just give you an example. Let's say you're out hiking, okay? So you're climbing up this mountain. All right? You start at, your elevation is 0 feet. And when you get to the top, you're at, I don't know, 1,200 feet. This is not really a mountain, okay? At some point, are you at 800 feet?
Yep.
Yeah. Are you at 600 feet? Are you at some point in between every, like at a number between 0 and 1,200, right? Because you have to walk on a continuous path all the way up to 1,200 feet. That's what that's saying, is that you can't skip a y value if you're on a continuous path like this. Think if the mountain goes like this. Here you are, starting down there at 0. And let's say this is like 400 feet. If you go from the bottom to the top over here again at 1,200 feet, are you at 400 feet at least once?
Yes.
Are you there more than once?
Yeah.
Yeah, okay. Just if it's a continuous function, you can't jump over any of those things. So if we're talking about a value, a y value in between these other two, you have to touch it at some point. So graphically, what we are looking at, like let's say I give you f of -2 equals -6, and f of 3 equals 5. Somewhere in between -2 and 3, you have to touch the x-axis, right? Think about it. -2 is -6. 3 is 5. We don't know what the graph looks like. You can do whatever you want, but at some point you've got to hit the x-axis, right? To get from a -6 up to a +5. That's all the intermediate value theorem is telling you, that you can't skip over any numbers. Okay? Okay, so let's try. The next one. For some continuous function f, we know that f of negative 3 is 5, and f of 2 is negative 3. What's the minimum number of values possible for a that satisfy f of a equals 1? So let's make a little picture. So f of negative 3 equals 5. That means when x is negative 3, y is 5, right? And f of 2 is negative 3. And I am asking you about this equaling your function value equaling 1. Okay. I do not know what the graph does. It could be some sort of crazy oscillating function that goes up and down a million times before it hits this. And you could cross that blue line over and over and over. We don't know how many, but are you crossing it at least one time? You're going from a positive 5 to a negative 3. Okay, so that's the minimum. The minimum number of values is 1. Thomas, you look perplexed. Okay, so let me draw my picture again. So f of negative 3 was 5, which is up here. F of 2 is negative 3. I want to know f of a equals 1, so that's a y value of 1. To get from this point to this point, I don't know how many times it's going to cross that blue line, but it's got to cross it at least once, right? So the minimum number is 1. There could be 10 different a values that give you 1, but there's for sure 1. That's all we know. Okay? All right. So let's look at this one. Same idea. We have a continuous function. It's super important that that is mentioned every time we're doing this. G of negative 4 is negative 10. So let's plot that. This graph is really weird for plotting that, but we'll go by 2's on the y-axis, okay? So negative 4, negative 10, that's somewhere down here. And then negative 1, 3. Okay, explain why g of x must have a root or an x value in the interval negative 4 to negative 1. A root means that it's crossing the x-axis. So what do you think? Explain to me. How do I know that my graph is going to cross that at least once?
Because it's continuous and the y values have 0 between them, so that's just 0.
Exactly, yeah. And guys, just in your own words like that, that's great. We know it's a continuous function. G of x. You can say something about the y values. Write it with an inequality. We could say negative 10 is less than 0 is less than 3. So, 0 has to be in between there. Doing okay? All right. Does it seem too simple?
Yeah.
That's good. It is that simple. It looks scary when you first read the formal definition of it, but it's not hard.
What do you do with the negative 4, negative 1?
So that is your x values. So like, see how we did g of negative 4 and g of negative 1. It's just saying like between here and here, is it going to cross the x-axis? It's going to have to. If you're connecting this point to this point, it's got to cross that x-axis. Okay? All right. Let's look at this one. We're almost done. Okay, you're waiting for a bus. There's a car traveling at 65 miles an hour, and when he notices you, he instantly slams on the brakes and comes to a stop. Well, that's good. He must have slammed on the brakes very hard. So true or false? While braking, the driver traveled at every intermediate speed between 65 and 0. Yeah, right? You can't skip over a speed when you're slowing down, can you? Okay, so true. Must the graph of this situation be a continuous function? Yes, you cannot skip speeds. We're not going to do... I mean, it's the same thing again. With it being continuous, you know it has to touch all of them. So, last thing, I want you guys to come up, and you can talk to each other, come up with a problem that is something you're interested in, where you can see the IVT being used. Okay? I know, your brains are tired today, but you can do this. So, I'll give you a second.